Honors Chemistry, this is your Day 6 lesson 4 on the basic atom. So electrical force is the single most important factor in all of chemistry. So the key point about electrical force is that positive attracts negative and negative attracts positive. Positive repels, pushes away positive, and negative repels, pushes away negative. So if you've ever played with magnets, you know that the North Pole and the South Pole attract each other. And the North Pole and the North Pole, two North Poles will push each other away, repel, and two South Poles will push each other away. So it's a similar concept. Electricity and magnetism are related to each other, but not exactly the same thing. But this is really a key fundamental concept of chemistry that really everything we talk about deals with this attraction-repulsion principle. Really, chemistry can be boiled down to two fundamental principles of nature. That positive attracts negative, and that things tend to want to move from higher energy to lower energy. So when you hold your pencil up in the air and you release it, it's going to fall from higher potential energy where your hand is down to the floor, which is lower potential energy. It doesn't fly from your hand up to the ceiling, which would be from certain potential energy up to a higher potential energy. So those two principles, positive attracts negative and things tend to move from higher to lower energy, are really the two guiding principles in all of chemistry. An element is pure matter that cannot be divided into simpler substances. So there are 90 naturally occurring elements plus another 28, approximately 28, that were created by scientists in labs. All matter in the universe is made of these 90 elements. Below are 5 naturally occurring elements: carbon, gold, neon, which is a gas, uranium, which is very radioactive, and mercury, which is one of only 2 elements that is liquid at room temperature. Just talk a little about each of these. So carbon. Carbon comes in many forms. It's indispensable for living organisms because it allows us to form long chain-like molecules. And we'll talk about that at a later time, but it's almost unique in its ability to do so. Carbon comes in a lot of different forms. Not only does it form the backbone for a lot of molecules in your body that make up living organisms, but it's what diamond is made out of, the hardest substance on Earth, and the graphite in your pencil. When you write with a pencil, graphite, which is very soft, is made of carbon because as you move your pencil across paper, it leaves a streak, and that streak is the graphite coming off from your pencil onto the paper. Interestingly, the graphite is the most stable form of carbon, not diamond, which is the hardest substance on Earth. That seems strange. But if you left a diamond out for 100 million years, it would eventually degenerate down into graphite. But carbon is to me, it's the most interesting element because of its versatility and how many things it's involved with. Gold is an element. Now, they've known about gold for thousands of years, but what they didn't understand was this concept of an element, that it's a substance that can't be subdivided down into simpler substances. We mentioned in class that the ancient Greeks thought the 4 elements were earth, wind, fire, and air. Or earth, wind, fire, and water. But that simply wasn't true, and they discovered that not too long after that. Neon is a gas in its natural form. It's what's called a noble gas, and we'll talk about why noble gases are unique. Uranium is the largest natural substance that we know of, that it actually can exist without falling apart. Now, it is radioactive, which means it throws off little pieces of itself, but it can still exist. And mercury, as I said, is liquid at room temperature, and it's very dense. You can take a steel ball, a very heavy steel ball, and put it in a container of mercury, and it will float. The steel ball will float on the mercury because mercury is more dense than steel. We'll talk about that relationship between density and things, whether they float or sink, sometime later in this class. So just as the 26 letters of the English language can be arranged to make millions of words, the 90 elements can be arranged and combined to make millions of different substances called compounds. A compound is a substance containing 2 or more elements. There are up to 50 million chemical substances, and who knows, it could be more than that, it could be a little bit less, but I've come across that number, and we'll just say it's a whole lot. It's in the tens of millions, definitely. So water, consisting of elements hydrogen and oxygen, is the most common compound on Earth. Hydrogen, 3/4 of the entire universe is made of hydrogen. It's the most common element in the universe, and oxygen is the most common element here on Earth. So when you put the two of those together, you get the most common compound on Earth, which is water. The periodic table is a list of all elements in the universe. The periodic table is the centerpiece of the study of chemistry. And I often say it's the most amazing document in human history, because on a single piece of paper you can fit every element in the universe. And the fact that we know that, how we know there's every element, that we haven't missed some, we'll talk about when we get into the periodic table in more detail. But and why it has this kind of unusual shape to it. The rows are the way they are and the columns are the way they are. We'll talk about that as well. There's a method to that, and we'll discuss that. So Dmitri Mendeleev is credited with creating the periodic table. He did much of his work by laying out cards while riding trains around Russia. So just as you've seen people maybe playing solitaire or some card game by themselves, that's kind of what he was doing. And he was putting them in order in groups of columns that are called groups, by the way, that seem to have things in common. So if you look at the leftmost column, except for hydrogen, which is really kind of unusually placed, lithium, Li, sodium, Na, potassium, K, all have some common features. And so he put things that have common features in the same column, and then things in the same row have something in common as well. So that gives the periodic table this shape, and that's how Mendeleev was able to kind of lay these elements out. And any good scientific theory should give you the ability to predict. And his did. When he laid out these elements to the periodic table, he had gaps. He didn't know every element. Not every element had been discovered back when he was alive, but he was able to figure out where there should be some new elements showing up. He didn't have a name for them. Nobody had discovered them yet, but when they did eventually turn up, they fit exactly where he thought they should fit. And so the periodic table, as he was developing it, was able to predict elements that had yet been undiscovered. So the two main divisions are, one, the metals. That's the alkaline earth, transition, and other metals. That would be the far left column, the second column on the left, that entire center area of light blue, and then the purple area. Those would all be metals. Non-metals are the ones over on the right. That would be the ones that say non-metals in orange, plus the halogens. Halogens are also non-metals, but they have special characteristics in chemical bonding, and so they're given kind of their own name. It's the second to last column on the right. And then finally, noble gases have very unique properties when it comes to chemical bonding, and that's the little bit darker blue column over on the right hand side. But nonmetals, halogens, and noble gases are all nonmetals. In between the nonmetals and the metals are the metalloids. Metalloid just means it's kind of like a metal, kind of not like a metal. It's a little bit of a mix between metals and nonmetals. Those are famous for being used for silicon chips or for computer chips and chips, electronic chips in your cell phone. So the most famous one is silicon. That's why Silicon Valley is called Silicon Valley. And those are the metalloids. We really don't deal with those very much as far as their unique properties. That's something you would learn more in a engineering physics class, or a physics class that would study semiconductors and electronics. Down at the very bottom are two series, lanthanide and actinide, which we really don't talk about much. We don't deal with those rows very much. In fact, a lot of the elements on there are not even actual natural elements. Uranium is the largest natural element, and it's down, kind of covered up by that label down there, but it's down in the very bottom row. Representative elements, group group A. So those would be the first two columns, 1A and 2A, and the last six, 3A through 8A. Those are the elements that form valence electrons. And we haven't introduced that word yet. We will in just a few slides, but those are the electrons that actually create chemical bonds. So electrons in the transition metals, the light blue in the middle, they do not form valence electrons. But the electrons in the first two columns and the last six, which are called the representative elements, do form valence electrons, which are involved in chemical bonding. And that's really what chemistry is all about, is creating chemical bonds. In about 400 BC, a Greek named Democritus developed the idea that there was a smallest piece of matter that could not be further divided. The Greek word atomos means indivisible, cannot be divided. The smallest piece of an element is called an atom. So they had this philosophical discussion because they didn't have the tools or the techniques or the technology to be able to study it any further, about whether if you took a piece of gold, and if you, in theory, this is just called a thought experiment, you cut it in half, and then you took one of those pieces and cut it in half, and then you took one of those pieces and cut it in half, and you kept doing that, could you, in theory, cut the piece of gold in half forever? Or do you finally reach a point where you have a smallest piece of gold, and if you cut that in half, then it's no longer gold, it's something else? So Democritus, among others, thought that no, there is a smallest piece beyond which you cannot cut it and have it still be that element, gold or whatever element you're dealing with. So that turned out to be, in fact, true, although not discovered or confirmed till thousands of years later. So in about 1800, English chemist John Dalton developed his atomic theory describing atoms and how they combine to form compounds. So here are there's 4 parts to Dalton's theory. All elements are composed of indivisible atoms. Atoms of the same element are identical. Atoms of one element are different from those of another element. Atoms of different elements can combine in whole number ratios to form compounds. That's combinations of 2 or more elements. And 4 chemical reactions are when atoms join, separate, or are rearranged. Atoms of one element cannot be changed into another element. The following are some notes concerning Dalton's 4 principles, so we'll take them one at a time. 1. Elements are composed of indivisible atoms. Dalton developed these 4 postulates 100 years before the discovery of protons, neutrons, and electrons, which we'll discuss in just a few slides. Dalton is correct that atoms cannot be divided into simpler substances. However, they can be divided, they can be split, and that's called a nuclear reaction. And only very large atoms, generally speaking, can be split. Not totally true, but generally it's very large atoms that can be split. So they can be divided, but generally speaking, we do think of atoms, as we talk about them here in chemistry, as being indivisible. 2. Atoms of the same element are identical. Atoms of one element are different from those of another element. That is true. The second sentence is true. The first sentence is not totally true. They're generally identical, but they can have differences, and we will talk in this lesson and the next what those differences are. So 2 atoms of the same element can be different in certain ways. We'll talk about that a little bit later. So Dalton did not know the concepts of ions and isotopes, to be discussed later, though that's what I'm referring to, and we'll talk about those later on. Number 3, atoms of different elements can combine in whole number ratios to form compounds, combinations of 2 or more elements. That law is completely correct. An atom cannot be divided and formed to form a chemical compound. This is why it's possible to have H2O, but not H1.5O. In other words, you have to have either 1 hydrogen or 2 hydrogens or 3 hydrogens. You have to have either 1 oxygen or 2 oxygens or 3 oxygens. You can't have half of an atom forming a chemical bond. So Dalton was correct on that. 4. Chemical reactions are when atoms join, separate, or are rearranged. Atoms of one element cannot be changed into another element. The first sentence is completely correct, and it's really what chemistry is all about. Rearrangements of atoms is the definition of chemical reactions, either joining them together, separating them, or rearranging them from one compound into a different compound is really the essence of what chemistry is. Atoms can, however, be changed into other elements. This occurs during nuclear reactions, which involves changes in the nucleus. We'll talk about that briefly, but it's really not chemistry, it's really nuclear physics. But we'll talk about a little bit about how nuclear reactions take place and what they are and how they happen. An atom is the smallest piece of an element there is. So if you cut an atom of gold or iron in half, you will no longer have gold or iron, and that's what we talked about. An atom consists of three parts: proton, which are positive charges, neutrons, which are no charge or neutral, and electrons, which are negative charges. So let's look at the structure of an atom. The center of an atom is called the nucleus. Unlike the nucleus that you learned about in biology, the nucleus of a cell, it doesn't have a pouch around it, or it's not in a container or a pouch. It's just a collection of protons and neutrons in the center of the atom. Orbitals, also called shells, are energy levels where electrons move around. Protons are positively charged particles in the nucleus. Neutrons are no charge neutral particles in the nucleus. And electrons are negatively charged particles that circle the nucleus, and really it's better to think that they fly around the nucleus, kind of like flies in a room. They seem to move around and buzz around kind of randomly. They don't really move around in a circle the way the Earth goes around the sun. They really just kind of fly around and buzz around, but they are outside of the nucleus and they move around at very high speeds. So a valence orbital is the outer orbital of an atom. Because helium has only one orbital, that is the valence orbital. Valence electrons are the electrons in the valence orbital. It is the valence electrons that form chemical bonds, to be discussed later. So this word valence, you're going to hear it 5 or 10 times in every class because it's central to atoms bonding with other atoms. What does it are the outside or valence electrons. It's not inner electrons. It's only the outside electrons that do that. And so that word valence is very key in chemistry because that's where the bonding between two atoms takes place, in the outer orbital and the outer electrons. So let's look at each of the three subatomic particles individually. So a proton is the positively charged part of an atom. You don't need to understand what positive means other than it's simply the opposite of negative. They could have called it the up and down particle. They could have called it the yes and no difference, but they decided to call it positive and negative. A proton has a mass of, you see the number there, 10 to the minus 27th kilograms, which is about 1,836 times more massive than an electron. So a proton has the same charge as an electron, but opposite, equal charge, but opposite. However, it's much, much more massive than an electron. A proton has a charge of 1.602 times 10 to the negative 19th coulombs. Coulomb is simply a measure of electric charge, which is a number we will rarely use. More commonly, we assign a charge of +1 and a mass of 1 atomic mass unit to a proton. So rather than using these rather ugly scientific notation numbers, unless we're actually doing some very precise calculations, they simply define a proton as being a charge of +1. And they define its mass as being a mass of atomic mass, as being 1 atomic mass unit. There's a technical definition of an atomic mass unit, but for our purposes, we can simply talk about an atomic mass unit as being the mass of a single proton or a single neutron, which both weigh essentially the same thing. Protons contain the strong nuclear force which holds them together in the nucleus against the repulsion of the electromagnetic force. So I demonstrated in class how two protons, if they're pushed gently together, will repel each other because they're both positive. But if you can push them together with enough energy, and this is millions of degrees of temperature, enough energy created by millions of degrees of temperature, you can smash them together hard enough so that they'll stick. It's like they have hooks. And if you can get them close enough together, those hooks will latch onto each other, the hooks of two protons, and they'll stick together. They won't push apart, even though the electrostatic force says they should push apart, positive, positive. So that's called the strong nuclear force. It's the strongest force in the universe, and that's why protons in a nucleus don't just fly apart. They stay together because they've been forced somewhere, sometime, a long time ago, inside of a star to be pushed together by millions of degrees of energy. Or as I told you in class, if it's a very large element, it takes a supernova explosion to create the very large elements, and that pushes the protons together. An electron is the negatively charged part of an atom. An electron has a negative charge equal and opposite to that of a proton, which is 1.602 times 10 to the negative 19th coulombs. So an electron is much, much smaller than a proton. However, the charge on it is the same. It's just opposite. So that's why they attract each other. And again, even that doesn't explain to you why do they attract each other, but you just, it's just taken. You don't need to understand it any deeper than that positive attracts negative. An electron has a mass, there's the number, 10 to the minus 31 kilograms. You don't need to know that number. An electron moves outside the nucleus in specific energy levels called orbitals. We talked about that. Think of orbitals like steps on a ladder. If you're climbing a ladder and you're standing on the first step, and then you want to go up to the second step, you have to bring your foot all the way up to the second step and lift yourself up. If you only go halfway up to the second step and then try to step down, your foot will just come back to the first step. You can't stand in between the first and the second step. You're either on the first step or you're on the second, and if you don't give yourself enough energy to climb up to the second step, you're going to fall back down to the first. It's the same with electrons in orbitals. Those orbitals are like steps. So an electron can't move in between orbitals. It has to move either in one orbital or the next higher orbital or the next higher orbital above that. Okay, a neutron is a part of the atom that has no charge. In the simplest sense, a neutron is made up of a proton plus an electron stuck together. So when you have the plus charge and the minus charge stuck together, they neutralize each other. It produces no charge. A neutron has a mass of, and there it is, and it's approximately the same as a proton, not exactly. This is slightly more than the mass of a proton, but not exactly equal to the mass of a proton and an electron added together. Anyway, that's kind of trivia. You don't have to understand that. Here's what you just need to understand. In chemistry, we assign a charge of 0 to a neutron because it has no charge, and a mass of 1 to a neutron. That's the same mass we assign to a proton. So for our purposes in this class, and there's no trick questions that are going to try to get you on this, you assume that the mass of a proton and a neutron are exactly the same, and we simply call that one atomic mass unit. Neutrons contain the strong nuclear force which holds protons together in the nucleus against the electromagnetic force. But what it doesn't contain is that positive charge that's going to push them apart. So it has the hooks to hold the protons together, but it doesn't repel them in any way. So that's why neutrons actually stabilize the nucleus. It adds those strong nuclear force hooks to the nucleus to hold the protons together and to keep them from flying apart. For that reason, you find that the nuclei of most elements in the first roughly half of the periodic table have roughly the same number of neutrons as protons. Not exactly, but roughly the same number of neutrons as protons. Chemical reactions create new substances by arranging atoms into new compounds through a chemical reaction. Example, take the reaction 2H2 plus O2 produces 2H2O, which, by the way, that's the way that reaction would be read. Water is comprised of 2 atoms of hydrogen and one atom of oxygen. A chemical change occurs when the atoms combine to form a structure called a molecule. Because water is made up of more than one different kind of element, it is referred to as a compound. So let's take a look at this. This is that reaction. This is what's happening in terms of a diagram of this. This is called, by the way, has a name called a particulate diagram. It's just a picture of the chemical reaction as it's taking place. So let's look at this. What you have there with the 2H2. So take the small 2 behind the H. What that means is that you have 2 atoms of hydrogen that bond together to form a molecule of hydrogen called an H2 molecule. Hydrogen, along with oxygen, are two of 7 different molecules, or I should say elements, that like to form molecules. They don't exist by themselves. You won't find just a hydrogen atom or an oxygen atom floating around in the atmosphere. They always like to pair up with, in the case of hydrogen, another hydrogen, or an oxygen, another oxygen, to form what's called a diatomic molecule. It means 2-atom molecule. So the H2 with the small 2 means that you have 2 atoms combined to form an H2 molecule of hydrogen. The 2 out in front is called, just like it is in math, it's called a coefficient. And what it means is that you have 2 of those molecules. So you have 2 H2 molecules. So the little number 2 is telling you the number of atoms in the molecule. The big number 2 is telling you how many of those molecules you have. Oxygen, same thing. It means there's 2 oxygen atoms bonded together to form an oxygen molecule. You only have 1 of those, so you could put 1 O2. You could put 1 out in front of the O2, but you usually don't do that. Just like in math, if your coefficient is 1, you usually don't write it. Now somehow those 2 hydrogens in that oxygen molecule come apart. Now how do they do that? It's just good old smash mouth. They bash into each other and break apart. And when they do break apart, the laws of chemistry just say it's more favorable for them not to come back together in the way they were before, but to actually for the 2 of the hydrogens to jump onto that oxygen and form an H2O, and for the other 2 hydrogens to jump onto the other oxygen and form an H2O. And so what you end up with are 2 water molecules. And we'll talk about the mechanism of how do you know whether something's going to break apart or not break apart, and that gets into a later part of the course. Okay, so that's what that equation means. It's what's happening pictorially in a particulate diagram, how that is working and how that's taken place. By the way, the 2 elements, molecules on the left, that's H2 and O2, are called reactants, and the water that's produced on the right side of the arrow is called a product. So reactants are on the left of the arrow, the products are on the right side of the arrow. Okay, chemical reactions create new substances by rearranging atoms into new compounds through a chemical reaction. Water is made of 2 hydrogen atoms and 1 oxygen atom to form a new substance called water, H2O. The way water reacts with your body is totally different than the way pure oxygen and pure hydrogen react with your body. In other words, if you were to drink some liquid hydrogen and liquid oxygen, you'd probably kill yourself because they're hundreds of degrees below 0. They're really, really cold. So they're not going to react in your body the same way as H2O does. So eating the reactants and eating the product is not the same, doesn't have the same effect on your body. So the point is that it has a different chemical impact, not just with your body, but with anything it interacts with. The reactant are not the same as the product in terms of the way they react. Okay, physical changes determine whether a particular substance is solid, liquid, or gas. These are called states or phases of matter. So there are 3 states of matter: solid, liquid, and gas. Gas, by the way, has nothing to do with, in this sense, has nothing to do with the stuff that people put in their cars to make their cars run. That's gasoline. That's just the name for a particular chemical compound used to power engines. It means it's a vapor. It means the molecules are separated, and we'll talk more about that at a later time. But has nothing to do with gasoline. So solids, the molecules are held firmly together. In the case of water, we call this ice. That's what ice is, when those 2 water molecules are held tightly together. They can't move around. They can wiggle back and forth, but they can't actually move apart. Liquids, the molecules touch, they stick together, but they can move around one another. So that's why liquid water will splash around. You can slosh it around in a glass. The water molecules are staying together, they're staying in touch with each other, but they're moving around. Finally, gas, molecules have enough energy to separate from each other and move upward against gravity. So that would be water that's evaporating, or if you have water on a stove, it's boiling. And that's boiling water would be steam, that would be water vapor. Okay, a nuclear reaction is one where the number of protons or neutrons are changed. So chemical reactions deal with the electrons, and there you see an atom, doesn't matter which atom that is, with two orbitals. So it's actually an oxygen atom. So the outer orbital, that second orbital, the one that's furthest away, those are the ones that really do the chemical reaction, those electrons out there in that second orbital. And that would be the valence orbital in the case of this oxygen atom. It's the outer orbital. The inner orbital with the two electrons in it really doesn't play any role in chemical bonding. So a nuclear reaction is one where the number of protons or neutrons change. If number of protons changes, elements are defined by the number of protons, not number of neutrons or electrons. So if a proton is added or removed from an oxygen atom, the atom will no longer be oxygen. If you added an atom to oxygen, it would become fluorine. If you took one away, it would become nitrogen. So it would actually change the identity of the element. Having said that, it's impossible to add or take protons away. The strong nuclear force is just simply too strong. There's no man-made way to split an oxygen atom. There is, however, less stable large atoms like uranium. You can split those and change the number of protons in the nucleus of a uranium atom. Number of neutrons change. The number of neutrons in two atoms of the same element can be different. These are called isotopes. So carbon has 6 protons. It has to have 6 protons in order to be carbon. And we'll go over the periodic table and you'll know how we know that carbon has 6 protons. Most carbon atoms also have 6 neutrons, but some have 7 or 8 neutrons. So these different atoms are isotopes of carbon. So that's what an isotope is. It's the same element, but it has a different number of neutrons. Now, ions we're going to save to a different letter, really to a different lesson. Really, ions are more important than isotopes, and we'll talk about those at a later time. Okay, so that takes care of this lesson. So go ahead and answer the questions. There's no answer key for these questions because every answer is in this video. And so go ahead and watch that and do that. And it would be good for you to have that done by Monday. Have this assignment. This is the day 6 assignment. Have this done by Monday, and I'll give you a new assignment for the third period. You'll get a new assignment on Friday, and first period you'll get a new assignment on Monday, February the 8th. Okay, have a good day and have a good weekend.